I want to show two more examples and then I'll close. And the two examples I want to show you is failures of fatigue samples in all of the structures are not limited to materials. We have design issues, manufacturing issues, maintenance issues, all of the things that go along with those. And so I want to show you two examples. I've taken these from an industry that's very important to Colorado, and it's also a passenger transportation system. It's called the aerial tramway industry. And I want to point out to you, this is that if you look at statistics in this industry, their number of deaths per passenger mile are much lower than the car that you drive to go to work every day. And so while I'm showing you these, that's my caveat, that they are very, very safe. So let's look at a design example, and then I'll let you think back to the beginning of my talk where this comes together. This is the fatigue failure in a bull wheel axle shaft. So what's a bull wheel? So in a ski lift, you have a wheel at the top and a wheel at the bottom, and the rope goes around and the people ride up and down. One end is a drive end and the other end is a counterweight end. And on the counterweight end in the schematic drawing in the lower, you'll see that you have a counterweight that provides tension to the wheel. And that allows one of the wheels to move to accommodate thermal expansion from the morning to the afternoon, as well as a change in the load from no loaded when you first get on it to a fully loaded lift. Is that assembly on that upper left-hand picture can move up to 20 feet or so during a day, simply to accommodate changes in the length of the rope. The failure we're looking at is in the shaft. That's in the shaft in the middle. And here's an example of the failure. There's the failure of the shaft. And it's a reasonably good size. It's a 13 centimeter design bar. Here's the end of the fracture surface in the upper left-hand corner. And you'll see it has all the characteristics of a fatigue crack. Cracks are perpendicular to the axis, which tell you it was failed basically in bending, rotating bending. The initial design is showed you with the shaft that's shown in the middle schematic, where the shaft was rigidly attached to the wheel and had the bearings on the end, such that with each rotation you got a point A. Look at point A and the shaft in the middle figure at the top. That point went from tension side to compression side to tension side on each cycle. Where have we seen that? I think that's what Whirler did in 1800s. And so what was the solution to this? The solution was simply to take and move the bearing to a different point, such that now we've gone from a stress distribution shown in the middle one, which was a high amplitude, to now a material that has a relatively low amplitude. And as long as you control the mean stress less than the fracture stress, the things last. Luckily in this case, that shaft was fully constrained inside the housing, so it made a lot of racket and became unstable but did not fall down. Let's look at one other case. I mentioned that residual stress is very important. Manufacturing can introduce unanticipated residual stresses that may be something that you don't want to happen. And so the example I'm going to look is the failure of a chair bale. And the chair bale, if you look at this as a chairlift, it's made up of three parts. There's the chair that the people sit on. There is the hooked piece that looks like a half moon that's attached to the chair. That's called the bale. And then there's the vertical piece that goes from that up to the rope, and that's called the hanger. And the failure we're talking about is in the bale, which is the bent tube. It's a steel tube that's bent to form that upside down U. So if you take that sample and you apply the force application system to it, as you see on the left, then the right-hand side is, you can go back to your freshman statics, do a free body diagram, and look at the force distribution in this part. The schematic drawing on the right shows you where the fracture occurred, and there's a tube, and the tube shows three tabs, and the purpose of those three tabs was to provide resistance inside the clamp. There's a clamp around those, and those three tabs kept the tube from moving back and forth. There's a rubber liner inside there, and that's the only purpose of those 3 tabs. But there's the location, so that's what we're going to look at in terms of a fracture. But think about the free body diagram. Think about fatigue. This is my homework. We'll have a quiz on this. Is what type of loading exists at the place in that horizontal beam at the top where the stress was applied? Well, I'll show you. If you did this and you said, what kind of loading from statics that you simply do is you would think that that force distribution would put the upper piece in bending, like what I've shown you there, and the bending would put the top surface in tension and the bottom surface in compression. Then, as the first graph shows you stress versus time, tensile stress due to the chair weight would give you the horizontal dashed red line. And then as you put the people on and took them off, you would get the cyclic load superimposed on that, but the tension would be at the top. Let's look at how it failed. Here's the picture of the failure, just to give you 2 images. The fracture, the upper image shows you the failure while the 2 halves were still, the upper ends were still welded to the chair. So that's after they were fractured. And the lower is after the sections were cut off the tube and laid on the ground. First thing you note is the fracture is about as perpendicular to the axis of the tube as you could draw, which suggests to you that the maximum stress is parallel to the axis of the tube. And secondly, as you see some offset at the upper, what does that suggest? That suggests to you that there was probably some residual stress of the part that was relieved once the part failed. Here's the nature of the fracture. The fracture nucleated at the bottom of the tube where the weld was, not surprising. That's not the issue. How did it grow? It grew up. It did not grow down. And so the question is, why would a beam in which you put in bending, where your first schematic of a free body diagram said the upper part should be in tension, why did the crack grow down? Well, here's the input. When this was fabricated, it was in 3 pieces. The bale was formed, and then when it was welded to the chair, it had to be physically opened like a chicken wishbone and put back on. And as a consequence of that, you put an imposed residual stress at the bottom of the tube, right where the crack started. Then you put the force application system on it. What happened? And each time they put on it, you took the load off. That gave you the amplitude, and the residual stress gave you the peak load. And the net result is you got a fracture. So here's a case of residual stress that was backwards. Well, I wanted to show you those 2 as examples of sort of what the issues. I have 2 more slides. What about the new materials? What about the future? Julie showed us all these new techniques that we can use to evaluate materials, and I think that there's a lot of opportunities there. And so I took one example from Brad Boyce's group at Sandia, where they've been looking at fatigue of nanomaterials, and these are electroposited nickel alloys with grain sizes less than 100 nanometers. And what they have observed is the traditional cyclic damage processes are inhibited by the ultra-fine grain material, and they get fatigue lives that are well above 10 to the 7th. But also they observe that during deformation or during loading, they get abnormal mechanically induced grain growth. And an example of which is shown you in the micrograph in the lower left-hand corner, where you see associated with the fatigue rack zones of very, very large grains. And so in there, their model for their papers suggests that at the top is the first case of fine grain material. Item B, with loading, you get mechanically induced growth, grain growth. The mechanically induced grain growth facilitates operation of crack nucleation mechanisms such as generation of intrusions and extrusions, and that then leads to the development of a fatigue crack. So here are some interesting things where the new materials that we're now seeing evolve may really bring to us features that need the techniques that Julie talked earlier about how you're going to really look at the fatigue behavior of those parts. So what I tried to do today is I want to show you that fatigue is not dead. Fatigue is a function of multiple variables, material, but design, manufacture, operation, and maintenance. What opportunities do we have as engineers? Many. You can have clean, defect-free material. The Timken data really pointed that out. Enhanced models to describe complex contributions. I think there's opportunities to develop realistic models that actually describe behavior. We need smart inspection techniques. The one lucky thing that fatigue cracks give us is that opportunity where you can have a fatigue crack develop and it provides you the opportunity to try to find it before it goes unstable. So and then many other. However, I still think one important thing that we can't overlook is fatigue education. We still need to teach what I'll call good common sense engineering. How many of you have checked the torque and the lug nuts on your car after you had new tires put on them? Okay, there's two. Well, that's part. When you get your new tires, they say on there, check lug nuts in 7 days or something. Why is that? To make sure they're tight. Have we learned anything? I started out with that as a question. I think we've learned a lot. Fatigue failures are less, and I think we see that. Certainly we've got lots of papers at this conference that are certainly doing that. But let's go back to where I started. We'll go back to the literature, the current literature. This is from September 12, 2016. Fan blade metal fatigue cited in Southwest engine failure from the NTSB. Folks, we're not done yet. We've got a few opportunities to go. So that's my comments in terms of fatigue, and I want to close with simply acknowledging the support of our industrial base at our Steel Research Center at the Colorado School of Mines. And thank you all for listening. I appreciate it.